Alright, hey guys, Chemistry Club here, and today we'll be covering measurement and significant figures. So, one thing we know for certain about measurements is that they are never fully accurate. So even if we were to make a machine so precise that it could measure lengths in atoms, it's still not fully accurate, and you're wondering why is that? And that's because of the Heisenberg uncertainty principle, right? We covered that last lesson, and that states that we don't know the position and velocity of an electron at any given moment. So, because of this, we have to round, and that brings us to the topic of significant figures. So when you take note of a measurement, you want to write as many digits as allowed by the increments on your instrument, and then add another rounded digit at the end. And this final digit is uncertain, but it is your best guess. So practice makes perfect, so let's take a measurement with this ruler. What would the measurement be if an object was long enough that its tip was at the arrow? So first, let's write down all the digits we know. We know it's somewhere in the 8 centimeter range. The ruler shows us that. And we also know that it's somewhere in between 8.7 and 8.8 centimeters, which again, the ruler has increments for. So we'll say 8.7 and round up to the next digits. So these are our known digits, because the ruler shows us increments which allow us to make these observations. So now, we add one uncertain digit. In this case, it would be our guess as to how far in between 8.7 and 8.8 centimeters the arrow is. So one thing to note, since at this point the increments are very small, we can't round to a greater extent. Our eyesight isn't good enough for us to make an accurate enough guess, like saying that it's around 8.73 centimeters. So all we can really do from this distance is tell whether the arrow is on the increment or in between it. So our final uncertain digit will be a 0 or a 5. And depending on how well you can see, this will change, but remember to be logical and never overestimate. So anyway, for our problem, since the arrow is in between the 8.7 and 8.8 centimeter mark, we'll say 8.75 centimeters. And remember, always put your units down. And that's how you measure it using significant figures. So next, we'll talk about how to count significant figures. So I'll just refer to them as sig figs from now on. Same thing, significant figures, sig figs. So there are a few rules to this. One is that all non-zero digits and zeros between non-zero digits are significant. So they'll go towards your count of how many significant figures are in a number. And next, all zeros to the left of the number are not significant, they are just placeholders. So for example, if I gave you 50, you could also write it as 00050, right? You can put as many zeros to the left as you want, but it doesn't really matter because the final number is going to be the same. So you can see that it doesn't really matter how many zeros I put at the end, or on the left of the number is still going to be the same, and thus those zeros are just not significant. And the third rule is that all zeros placed to the right of the number are significant. So you'll want to remember that measurements can end in zeros. And by writing them down, it's a conscious effort to note that that zero there is significant. So a fourth rule that sort of ties into this third rule, so if you have a number bigger than 1, like let's say 600, right? If you have a number bigger than 1, like 600, and those last two or last one, however many digits there are, they end in 0. You have to have those zeros there in order to express the number the way it is. Right? You can't say 600 without putting those two zeros there at the end. So then that brings us to the question, how do we indicate significant, or whether the numbers are significant or not? And the answer lies in the decimal point. So if we have a decimal point after the two zeros in the 600, then we say that all three digits are significant, because that shows us that the measurements taken was just happened to be exactly 600. Whereas if we're saying 600 without the decimal point, that's just a rounded number, right? So we only say that there's one significant figure. And our final rule is that all exact values have no significant figure. So for example, a meter, right? This is a known value. We know a meter is exactly 100 centimeters, right? So we can put as many zeros after the 100 as we want, but it'll still be exactly 100 centimeters. So the sig figs doesn't really matter in this one. These conversions have no significant figures because they have infinite significant figures. So let's do some practice to make sure we have this down. Our first example is counting the significant figures in 505.0. So let's go through the rules and see what we can do. Our first rule indicates that non-zeros and zeros in between non-zeros are significant. So with this, we can say that the 505 will be significant. So that's 3 digits so far. And we don't have any zeros to the left of the number, so the second rule isn't necessary here. Our third rule states that zeros to the right are significant, and we have 1. So that brings our count to 4. Since we have a number after the 0, the fourth rule doesn't apply. Again, because we don't have that 0 ending there, right? So we don't have to indicate with the decimal whether that 0 is significant or not. So in this case, the fourth rule isn't there, so we don't really have to consider it. So all in all, we have 4 significant figures here. Our next question is how many significant figures are in 0.003190450. So that's a big number, so let's go through each rule and figure out what we can do. So with rule 1, we can see that the 319045 is significant, right? Non-zeros and zeros in between non-zeros. And with rule 2, that's inapplicable. Rule 2 will show us that the zeros on the left of the number are not significant. So we won't have those towards our count. So we're still at 6. And rule 3 makes the last 0 significant, right? We know that it's a conscious effort to make that 0 significant because the measurement just happened to end in 0. And rule 4 isn't applicable here, again, because the number is a little smaller than 1. So our final count is 7 significant figures. Our final question is how many significant figures are in 500 million? Or is that's 500 million. So let's tackle this step by step. Step 1 will give us the 5, that's significant, so we have 1 digit. And step 2, we don't have any zeros to the left of the number, so that's inapplicable. And rule 3 will say that we have 8 more digits that are significant, right? Those zeros there. But remember, rule 4 says that without the decimal, these numbers don't mean anything. So we're still left with the 5. So that's just 1 sig fig. So here is a challenge problem that I'd like you to think about on your own. So once I reveal the problem, just pause the video like last time and just work it out and see what you can do. So, how do you represent 6,000 decimal point with 2 significant figures and not 4? So the answer is a bit unorthodox. Instead of writing it conventionally, what we're going to do is use scientific notation. Right? So if we say 6.0 times 10 to the third, that's the same thing as saying 6,000. But that will give us 2 sig figs, and that will allow us to represent that number, which we can't usually represent with 2 significant figures, in 2 significant figures. So remember, worst case scenario, if you can't express that amount of sig figs in conventional means, always use scientific notation, because it's there. And it's pretty handy sometimes. So let's talk about operations with significant figures. So first up, addition and subtraction. For these, you want to add and subtract normally, and then round to the least amount of decimal places in all the numbers that you performed operations on. So disregard all the numbers before the decimal point and just focus on what comes after it. So I'll give you one to try on your own and see. What is 5.555 plus 3.3 minus 7.7777? The correct answer is 1.1. So one habit that you really want to break is rounding first. So remember, these numbers are rounded perfectly the way they are, right? We write them down this way because we're indicating how many digits are significant, so you don't want to round past that. So you want to perform your operations first, right? You want to add those numbers first, and then once you get your final number, then you round to the amount of decimal places, which is the 3.3. So we're just going to put 1 decimal place here, but add everything first, and then round. So for multiplication and division, you're going to want to count the amount of sig figs in each number, and then perform your operations. Again, don't round first. Oops. And then, once you get to your final answer, round to the least amount of sig figs there are in your numbers that you just performed operations on. So with addition and subtraction, you only looked at numbers after the decimal, but this time you're going to look at the number as a whole. So try this one. What is 555.5 times 33.33 divided by 7.7777? The final answer you should have gotten was 2,381. So for this one, since 555.5 and 33.33 have four significant figures, your final answer will have four significant figures, and after doing the math, what I got on my calculator was 2,380.500019, which you round up to 2,381. So now since this is AP and SAT prep, what good would it be without a few sample problems from the test itself? So here's the last FRQ question from 2016, which is the one I took, and this I hope stresses how important sig figs are. Even though I got a 5, I slacked on sig figs and I actually missed this question. So I don't want you to do that. Study your sig figs, know your sig figs religiously, and questions like this should be fine. So a few things you want to know before you get into this question is how burettes work, or burets work in French. And burets are things that you measure how much liquid you pour. So you start out at an initial volume, which you can see in the one on the left, and then once you drain all the liquid that you need, you can get a measurement from the one on the right. And you subtract the final minus the initial to get how much volume or how much liquid was displaced from the bure. And another thing you're going to want to know, you may have heard this in your science classes already, but when you take the measurements of liquids, you always round to the bottom of the meniscus. So you can see how on the bure in the close-up, the water forms this U shape, kind of. It's more of a flattened U, but you can see the U shape. And you want to take your measurements at the bottom of the U. That's just convention, that's just how we do it. So anyway, I just want you to try part A on your own. Try part A and see what you can do. And then pause the video now, and I'll talk about the answer afterwards. Alright, so let's do this step by step. For the initial measurement, we have the given digits of 5 milliliters, and you can say the measurement is between 5.6 and 5.7 milliliters. However, since we are limited and how much we can see, your best bet is to estimate in increments of 0.5. So our initial value is going to be 5.65, right? You can see how it's in between the 5.6 and the 5.7. So since our vision is limited, 5.65 is your best guess. And our final value is going to be at the 37 millimeter mark. So that's one digit, and then we also see that it's exactly at the 37.3 mark, almost exactly. So we'll use 37.30 as a measurement. So this goes back to our rule, right? Increments of 5 and 0 because we're just limited in vision. So finally, to get our answer for the total amount of liquid displaced in the flax, or displaced in the bure, you're going to want to subtract the two. And what you get is 31.65 milliliters. So again, I can't stress how important sig figs are, but make sure you know these. Make sure you just know your sig figs. That's all I can say. So in the next unit, we'll be covering stoichiometry, which is probably the most important thing you'll ever learn in chemistry. So hope to see you then.